Hello everyone, we will discuss the problem place the numbers of division 1 and it is a very simple problem despite it being rated so high. So the problem says that you are given three stacks 1, 2 and 3 and you are given a set of numbers from 1 to n 1, 2, 3, 4. Suppose n is 7. So these are the numbers. What you need to do is you need to pick some elements, suppose 2, 4 and 6. You will add them to the first stack. You will pick some elements to add to the second stack and then some to the third stack. So maybe this and this are added to the second stack, and this um, 5 and 7 are added to the third stack. Also, like one element, all the elements have to be added to some stack, and an element can be added to at most like only one stack. So one can only be added to two or three or one, but like not to multiple stacks. So afterwards, what will happen is you will have the number um, 1 and 3 in the first stack. You will have the number 2 and 4 in the second stack. And you have the number, I think, 5 and 7 in the third stack. The problem says that these elements in the stack are ordered in an ascending order. So 1 will be at the bottom, 3 will be at the top. Here 4 will be at, like 2 it will be at the bottom, 4 will be at the top, and 5 will be at the bottom, 7 will be at the top. Basically, whatever is the largest element in this set, which is assigned to a particular stack, will be placed at the top. Also, the stacks can be empty. So, like you might not add anything to this one first stack. So, question asks you to find the number of ways in which you can, uh, add these numbers from 1 to n to the three stacks. There are total of 3 to the power n ways because there are n numbers and each element can be added to three stacks, any of the three stacks. Uh, so you need to find a number of ways in which you can add the elements to the stack such that the sum of the top elements of the first and second stack is equals to some m. M is given to us. So for example, if m was 7, then this is one valid configuration. Another valid configuration would be something like maybe 2 and 4 in the first stack, 1 and 3 in the second stack, 5 and 7 in the third stack. So this is the top of element of the first and second stack. Their sum is equal to 7. So you have to find all the possible arrangements. Another arrangement could have been something like 4, 2 and 1, 3, 7 and 5. So here there are three elements and the top element is 4, the second is 3. So you have to count all these ways. Actually, you have to find the probability, um, but that would simply be the number of ways divided by the total combination, which is 3 to the power n. So finding the ways is enough here. So how do we approach the problem? Well, it's very simple. There are two cases. The first case is when one of the stack is empty. So one of the stack is empty out of the first two stacks. So this is the first, the second and third. Let's assume that this is empty, okay? And we have this numbers 1, 2, 3 all the way up till n. And this is empty. So since the sum of the top two elements of the stack must be equal to m, then that means that this should contain the number m at the very top, right? Suppose the number m is somewhere here in the number line. So that would mean that any element like m plus 1, m plus 2, etc. cannot be added to the second stack because then it would be the new top element will change. It would be something greater than m, right? So m will be added to the second stack. All the elements greater will be added to the third stack. They cannot be added to the first stack because we are assuming that is empty. And for the remaining elements, for the remaining m minus 1 elements, they have a choice. Each element can either go here or it can go here. It will not impact the answer because suppose this 1 goes here, so it will come since the stack is ordered in an ascending order, this 1 will be placed below m. So the top of the stack will not change. So when the first stack is empty, there are 2 to the power m minus 1 ways. Okay. Similarly, if the second stack was empty, like there was something, the second stack was empty, so that would mean the first stack would contain the number m. It's basically just this case only. The numbering is reversed. So in that case, there would also be another 2 to the power m minus 1 ways, and the total number of ways will be 2 to the power m if one of the stacks was empty. Okay. Also, you need to make sure that m should be less than equal to n, because you want to place m in one of the stacks if m is greater than n. So if this, this is 1 to n and m is somewhere here, so that doesn't lie in this range, right? Only numbers from 1 to n can be added. So this is one part of our answer which has been calculated, and in the solution code, if you want me to show it, I have added this to my answer. I have added 2 to the power m to my answer. Okay. Now the second case. Second case, both the stacks have some element. So both stacks are non-empty. Suppose this is the first stack, this is the second stack, this is the third stack. We have numbers all the way from 1 to n. Suppose I this that so what we will do is we will try to iterate over all the possible uh, the only thing that concerns us is the top of the stack, right? So the top of the stack could be 1, the top of the stack could be 2, 3, 4, 5, it could be anything. So we will try to find like all the possibilities for the top of the stacks. So let us assume that the top of the stack for the first element is for the first stack is I. Then can you tell me what should be the top of the stack for the second stack? It will be m minus I, because the sum has to be equal to m. So if we look at it on the number line, suppose I comes here and m minus I comes here. We are assuming, this is our assumption, to make things simpler, that for now, let I be less than m minus I. That means on the number line, I lies to the left and m minus I lies on the right. Finally, we will like multiply this, whatever we get from this part, we will multiply it by 2, so that then we don't need this assumption. Okay. But for now, let's just go with this assumption that I is less than m minus I. So now this element, we have said, okay, this will go to the first stack. This element will go to the second stack. The rest of the elements we need to check. So can you tell me where will these elements go? The elements which are greater than m minus I. Can they go to the first stack? They cannot, because if they go to the first stack, then the top element of the first stack will change. They can also not go to the second stack for the same reason, right? So these elements all can only go to the third stack. So there is only like one way, one possibility for these elements, right? So let me, yeah. So for these elements, there's only one possibility. Now, what about these elements from the range I plus 1 to m minus I minus 1? What about these elements? Well, these elements cannot go to the first stack because they are greater than I. They can only go either to the second stack or to the third stack. Okay, because if they go to the third stack, see, whatever is in the third stack, we don't care because we're not talking about the top element of the third stack. But if they go to the second stack even, then they will be below, like they will not be the top element because they are less than m minus I. So all these elements have two each element has two areas, two stacks that it can go to. So it will be 2 into 2 into 2 into 2, which will be 2 to the power m minus I minus I minus 1, I think. Yeah. So like these much elements are between these two. So there will be 2 to the power m minus 2i minus 1 ways. What about these elements? I minus 1 elements? Well, these elements can go anywhere. They can go here, they can go here, and they can go here. Because again, the top doesn't change. So these have 3 to the power I minus 1 ways. Every element has 3 ways, so 3 into 3 into 3 I minus 1 times. So when we fix for some I, the total number of ways are 3 to the power I minus 1 into 2 to the power m minus 2i minus 1. Okay. What was our assumption here? Our assumption number 1 is that I is less than m minus I. Okay. The second assumption is also very obvious, that m minus I must be less than equal to n, because this is m minus I, right? It can m minus I cannot lie here, because it cannot be greater than n. So these are two assumptions. Now see, we are assuming I to be less than m minus I. Suppose um, our m was 5, okay, and we had some very large n value, and let's assume that the first stack had element 1 at the top, the second stack would have element 4 at the top. Or another case, so this is I equals to 1, and m minus I is 4. Second case is it can have 2, and this can also have, will have 3. The third case will be when this has 3 at the top and this has 2 at the top, and the fourth case will be when this has 4 at the top, first stack, and the second stack, I'm not drawing the third stack, and this has 1 at the top. So we are only calculating these two cases because here I is less than m minus I. So we don't need to and you can see that, the other two cases are also same only, just reversed. So if we just calculate this half and then we multiply it by 2, we are done. Okay. So what we want to actually calculate is summation I is equals to 1 to uh, some x value, uh, like for m equals to 5, right? I will go all the way till 2. It will also depend on the value of n, but suppose n is very large, or n is 100, right? So n won't be a bottleneck here. Uh, the value of I will be 1 or 2. It can not be more than that, because then this constraint will fail. So here x will be 2. But let's say there is some x, okay, till which we want to do the summation. So it will be summation 3 to the power I minus 1 into 2 to the power m minus 2i minus 1. Okay, one will be there. And you just need to find this summation. So the first thing you should do is you should maybe to check for correctness, um, you can just run a normal for loop and see if the answer is okay. Make sure that once you calculate this, you multiply it by 2. So this will be 2 into this thing, and then you add this to the answer as well for the first case. But let's try to derive a formula for this. It's very simple. See, 3 to the power I minus 1 can be written as 3 to the power I upon 3. All right. 2 to the power m minus, this can be written as 2 to the power 2i into 2, the summation, and then you're multiplying it by 2. So this 2 and this 2 cancels out. Uh, this will be 2i. This 2 and this 2 cancels out. 2 to the power 2i can be written as, okay, so since this m is a like common term, we can take it outside. 2 to the power m, this 3 also we can take outside, and this would be summation 3 to the power I upon 2 to the power 2i, and 2 to the power 2i can be written as 4 to the power I, basically 2 square to the power I. Okay, so this summation can then be reduced to uh, 2 to the power m upon 3 summation 3 by 4 to the power I. And if you know geometric progression, you can find the sum of the series. So the summation of this will be the first term will be when I is equal to 1 into this uh, multiplier to the power x minus 1 upon this is the summation of this series. Basically, if you have a series like summation a to the power I equals to 1 to the n, the summation is a into a to the power n minus 1 upon a minus 1. Okay, so this is the formula. And if you then open it, you will see, okay, this becomes minus 1 by 4. This becomes minus 1 by 4. This 4 goes to the top and cancels this, and you are left with 3 into 1 minus 3 to the power 3 by 4 to the power x. And you are also multiplying this by 2 to the power m by 3. So this will be multiplied by 2 to the power m by 3. These two also cancels out. So your final formula is something like this. Okay. Now the only issue is how do we find this x? Because uh, otherwise, if you don't know this x, you will have to do some looping, and like you will have to either run this loop. So if you want to find x, you can just look at these two constraints which I mentioned. The first constraint I mentioned was I is less than m minus I. So that means I will be less than m by 2. Okay. So suppose, but here there is a like small catch. Suppose m was equals to 4, right? Then in that case, m by 2 is 2. So I will be less than 2. Okay. But if m was 5, then m by 2 will be 2.5. But so I will actually be less than 2.5. That means I can be equal to 1 or I can be equals to 2. So for odd case, it will be m plus 1. So instead of writing it like this, you can write it like I will be less than m plus 1 by 2. This will work. Otherwise, you can handle the case separately for odd numbers. Okay. So this is the first constraint, and let me erase the part to the right so that's a little bit clear. The second constraint is m minus I should be less than equal to n, which is very obvious. Uh, Otherwise, the term will lie ahead of n and you cannot take it. So that means I needs to be greater than equal to m minus n. Okay. So this is basically the range of x. So I should be greater than equal to m minus n and I should be less than m plus 1 by 2. Okay. So I will actually lie in this range m minus n by 2 and m plus 1 by 2 minus 1 inclusive. Okay. So you want, like we had this series, right? We had this series. The series sum was something like this. So this sum was for x is equals to, like for I, this formula, let me write it, 2 to the power m into 1 minus 3 by 4 to the power x, right? This was the summation of um, whatever we had in the inner term for I equals to 1 to x. But here the I lies in this range. It doesn't lie in 1 to x. So you can just use do whatever you do for like prefix sums, right? So uh, what you want to do is you want to calculate the sum from I equals to 1 to m plus 1 by 2 minus 1, like for this range, and then you need to subtract that um, with the sum from I equals to 1 to m minus n by 2 minus 1 prefix, because the sum from L to R is, sum till R minus sum till L minus 1. So Sum till r will look something like this. Sum till um, L minus 1 will look something like this. Okay. This can be written as m minus 1 by 2 if you solve it. So this will be written as m minus 1 by 2. Okay. Also there is also one thing you need to uh, 1 second. I don't think there will be a 2 here. Yeah, I is only greater than equal to m by m minus n. So there won't be a 2 here. So it will be till um, m minus n minus 1. One thing to keep in mind here is that this will, instead of being m minus 1, this will be like maximum of um, like you can the thing to take care of here is when m minus n is uh, less than or equal to 0. Okay, so that case needs to be handled separately, because if m minus 1 is negative, like it would be, instead of being m minus 1, it would be um, maximum of 1 comma m minus n, right? Because uh, the like the smallest value of x possible is 1, because you're taking the summation from I equals to 1 to some place. Anyways, this you can handle separately. This is actually the proper range. I did this so that I could easily represent it in this formula. Otherwise, this term will never change. Here you might need to, uh, you know, here you might need to add some um, conditions. So if m minus n is less than equal to 0, then this sum will be equal to 0. Okay. Otherwise, this sum will be represented by this formula. That's what I'm trying to say. So then, like, that's all for the problem. In my implementation, what I did, since we were calculating the sum from sum 1 to r and sum from 1 to L, this is the upper limit on x and this is the lower limit on x, and I'm subtracting them. Um, if you look at the formula is 2 to the power m, 1 minus 3 by 4 to the power r, minus 2 to the power m, 1 minus 3 by 4 to the power L. So these ones will cancel out actually, and it would be 2 to the power m, 3 by 4 to the power L minus 3 by 4 to the power r. So I calculated it like this, and because I was calculating it like this, and uh, uh, and the reason I was able to get this because I was using this formula. So in this formula, we were assuming that the first term of the GP was 3 by 4. So x will at least be equals to 1. That's why I was doing here maximum of 1 comma m minus n. But if you don't want to do it like this, then you can calculate this value and this value separately using the uh, using this GP sum formula, and then you can subtract them. Just keep in mind that if this is negative or this is equal to 0, then the sum will be 0. Okay. That is all for the solution to this problem. I will show you my code. So I find the upper x, like lower limit on x and the upper limit on x, and then I am just I'm subtracting the uh, like sum till r minus sum till L minus 1. So sum till r will look like till the upper limit, and this is basically 3 by 4. Uh, it will be, you have to take care of mod as well. So yeah, if you're doing uh, 3 by 4 mod something, then this will be 3 into 4 inverse. And I hope you know how to calculate this. This will be like 4 to the power mod minus 2. This is called a modulo inverse of 4. And then you have to take the mod. So this is what I'm doing. I'm calculating the modulo inverse of 4, then I'm multiplying it, like raising it to the power of x upper. And this is sum of L minus 1. Like again, if this line confuses you, you don't really need this. Just tackle the case when m minus n is less than or equal to 0. So you need to tackle that case separately if you're not doing it like this. Okay. In that case, the v1 value will be 0. Otherwise, nothing will change. All right, that's for all for the solution. Thank you for watching.